in the previous subtopic when we discussed about first order system, the effect of each parameters to the dynamic response of the system. So we are going to do the same thing here, but somehow second order system is a little bit more complex than first order system. So let's discuss about the second order system a bit more in detail before we discuss on the effect of the parameters to the dynamic behavior. In general, second order system can be divided into 4 different categories depending on the value of the damping ratio, the zeta. So I will divide it into 4 different classes. If you still remember, I will write it down again here, the generic expression of a second order transfer function, k omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared. So there are 3 parameters, k, omega n, and zeta. I will classify second order system into 4 different classes depending on the value of the zeta. The first class is when zeta is greater than 1. In that case, we call that second order system as an overdamped system. So overdamped when zeta is greater than 1. When zeta is equal to 1, we call it as a critically damped second order system. And then the third class, when zeta is between 0 and 1, we have an underdamped second order system. The last class is when zeta is equal to 0, we will have undamped system. So overdamped when zeta is greater than 1, critically damped when zeta is equal to 1, underdamped when it is between 0 and 1, and undamped when zeta is equal to 0. Let's start it with the first one, overdamped when zeta is greater than 1. You still remember this expression? This is the characteristic equation of a generic second order system. And solving this characteristic equation, finding the root of this characteristic equation will lead us to the poles of the second order system, right? Still remember about this. So now let's take a guess of a damped system when zeta is greater than 1. This is a second order equation. So when you want to find the roots of this characteristic equation, basically you just find the roots of a second order polynomial using the ABC formula. You still remember about that, don't you? The formula to solve the roots of a second order polynomial. So using this ABC formula, I will write it down again here. If you have an equation that looks like this, the roots of this equation will be equal x1 and x2, let's say, will be equal to minus b plus minus square root of b squared minus 4ac plus divided by 2a, right? So you just use this formula to find the poles of the second order system. So in our case here, A is 1, B is 2 zeta omega n, and our C here is omega n squared. If you try to solve it, then you will get your roots S1 and S2 like this. Remember again, we have an overdamped case. Our zeta is greater than 1, so the one under this square will be greater than 0, right? Zeta is greater than 1, so zeta square is greater than 1 minus 1 is positive. So square root of positive number, you don't have problem, you have real number. So in this case, you have 2 poles where both of them, S1 and S2, are real number. I can rewrite the characteristic equation into this form. So we have 2 poles, S1 and S2 in here. And both of them are real number. Taking into consideration a stable system where all of your poles are in the left-hand side, left-hand plane of the S-plane. So if we sketch these 2 poles on the S-plane, both of them, the poles will be probably somewhere here and here. But both of them are lying at the real axis because the 2 poles are both of them real number. Let's take a second class when we have critically damped system. When that will happen if your zeta is equal to 1. We do the same thing, but in our case here, zeta is equal to 1. This is equal to 1. When zeta is equal to 1, after you apply the ABC formula, look at this, your zeta is equal to 1. If zeta is equal to 1, 1 square is 1, 1 minus 1, this will be 0. So what you will have? You will have twin identical real pole in this case. And your poles will be located at the same location. Your two poles will be located at the same location at negative omega n. If you sketch it in your S-plane, then you will have two poles exactly at the same location probably at this location. Remember, we only consider a stable system in this case now. So the two poles at the same location, both of them at the left-hand plane of the S-plane. These two are at exactly at the same position at the real axis. This is when you have a critically damped system. The third one is when we have underdamped system. Underdamped system will happen when your zeta is between 0 and 1. When you want to identify the poles, we treat the characteristic equation same like before. To find the roots of the characteristic equation, we apply the ABC formula. But look at this again. This is after you substitute all of the parameters to the ABC formula. This is the formula. But now our case here, we have underdamped. Our zeta is between 0 and 1. If zeta is between 0 and 1, zeta square will also be between 0 and 1. So it's less than 1. A value less than 1 minus 1, this will become, this part under the square root here will become negative. Square root of a negative number is, it's an imaginary number. So you will have poles which are complex. You will have a complex poles. The first pole is located at this location. This is the location of the second pole. Please take a note here. I just referred this part here, the one under the square root there, and then I put a notation of a imaginary number there, j, or you can use I. It doesn't really matter. I or j, both of them are the same. So what you see here, your poles are a complex number. If you look at it carefully more, the real part are the same. The imaginary part almost the same except the sign here. So what does it mean? This means the two poles, the two complex poles are the conjugate of each other. So the other pole is, one of the pole is the conjugate of the other pole. Okay, it's a complex conjugate to each other. So in this case, you will have two complex conjugate poles where the difference is only on the sign of the imaginary part. So if you sketch it on the S-plane, probably the location of these two poles will be like this. This is the first pole, this is the second pole. Both of them are lying at the same vertical location. Why is it like that? Because they have the same real part and the imaginary part is just only differ by the sign there. So in S-plane, it's just mirrored by the real axis here. That is the behavior of a underdamped second order system. The last class is an undamped system when your zeta is equal to 0. Same like before, again, when you want to find the poles of this second order system, you have to apply the ABC formula to the characteristic equation. But remember now, our zeta is 0. So what we have now is square root of -1, right? Which is again imaginary number of with a unit of 1. So the poles of this undamped system, if you analyze it from this ABC formula, you will get poles, complex conjugate pair of poles, but these poles are located at the imaginary axis. because if you look at this, there is no real part on it. The real parts are 0. So you will have two imaginary conjugate poles. Both of them are located at the imaginary axis. Okay, so these are the difference between these 4 classes of second order system: the overdamped, critically damped, underdamped, and undamped system.